Well, let's switch a little bit now to wood movement. We have normal wood movement, and then in a few slides I'm going to talk about well, it's normal for the tree, but for us we think of it as abnormal. Okay, here, if you learn nothing more than this, you've learned some great information. Wood does not change its size or shape. That is, it doesn't shrink, swell, warp in use except when its moisture changes. So anytime you have any problem of size change, warping, shrinking, swelling, you know the moisture changed. Absolutely, positively, no question about it. Now, the wood moisture changes when the surrounding relative humidity changes. Okay? Wood moisture does not change when the temperature changes if the humidity is constant. So in other words, people sometimes say, hey, that wood, they stored our cabinets out in the garage where it's really cold and freezing below zero. Temperature doesn't matter. We need to know what the humidity is. And if you've got your cabinets wrapped in plastic, no problem. It's the same humidity as when you wrapped them. Also, size or shape then does not change when the temperature changes if the humidity is constant, because constant humidity means constant moisture. Okay. Very key facts, those last 4 slides, very key facts. It's people that don't know those 4 facts that hire me. So now you don't even have to hire me to solve most of your problems. And here's a little chart that I require all my students to memorize. And let's start at the 80% relative humidity. If you have a room, if you have a home, a kitchen, an office, whatever, at 80% relative humidity, the wood will come to 16% moisture. And for reference purposes, we call that 16% EMC. And we're going to see 80% humidity on the average in a tropical island, a coastal climate, Miami, New Orleans, in a humid place, okay? For most of the United States, we're going to see 65% relative humidity. The average humidity in most of the United States, winter and summer, is 65% humidity outside, 12% moisture, or 12% EMC. Now, most of you folks are going to be making cabinets for interior use, which means the interior environment might get to 50% relative humidity on the average, but not much more humid than that. 9% moisture, 9% EMC. Well, yeah, there's some places that are a little more humid, New Orleans and Miami and Seattle, Washington maybe, but for most of the United States, 9% moisture is going to be the top value. And the lowest value is going to be 30% humidity. If it gets drier than 30, we start to get sore throat, chapped lips, all that, and we don't like it. We install a humidifier. So, well, now that it's a little different for like Denver and Albuquerque and so on, they do have a little lower than 30% relative humidity. But most of the United States, 6% is the driest a piece will get. And because when a piece of wood dries, it shrinks, it tends to crack and everything else. But when it swells, we don't see quite as many problems. We like to shoot for the 6 or 7% moisture in wood that we're working on, certainly in hardwoods. In softwoods, we have a little different issue. But now, we can actually calculate how much wood changes its size or shape when its moisture changes. So this little formula, delta D, change in size, equals a number, and this DI is the original size, times the coefficient, times the moisture content change. And the numbers, here's a whole list of, I just took a snapshot of some of the numbers that are available. And so if you know the species you have, well, here's commercial red oak, for example. Here are the coefficients that you would use in that equation, and you know the moisture difference, you know the original size, and you can calculate the change. Actually, you can do it the other way around. If you know the original size and the moisture change, the size change, you can calculate the moisture change. Now, we have some special wood movement because that formula is talking about normal, everyday wood movement. But some wood moves differently. Normal wood does not shrink along the grain, lengthwise shrinkage. Juvenile wood, remember, first 15 years of growth, tension wood and hardwoods, compression wood and softwoods can shrink like 3%, plus or minus. And then we can add to that the slope of grain. If the grain isn't perfectly vertical with the board, with the lumber piece that we have, but has an angle, then we're going to see some of that shrinkage lengthwise again due to slope of grain. Okay, I'm ready to switch topics here to bacterial infections. And again, remember, there are questions that come up at the end. So if you do have questions, if I didn't take long enough, fire your questions off. Bacterial infection. In a living tree, we get this bacteria that grows. It doesn't kill the tree. It's a special bacteria in that it's anaerobic, meaning it grows in no air conditions. You know, the bacteria we're familiar with, that you get a cut and you get a little infection, or, you know, those bacteria are all aerobic bacteria, but this is an anaerobic bacteria, kind of rare. Gangrene is one anaerobic bacteria, but we don't see or hear a lot about them. This bacteria, though, enters through the root system in most cases, and then it moves only an inch, inch and a half per year. So if it goes in the roots, it might take it 50 years to get up into the stem that we get to the sawmill and we begin to saw lumber out of. And because it's an anaerobic bacteria, it prefers wetter soils, and the slow growth, it'll be in older trees, and it'll be in the bottom of the butt log, the bottom log of the tree. Okay, so far you aren't too excited about it, but it secretes an enzyme, the bacteria do, that destroys and weakens the wood. All right, number two, it creates fatty acids. You say, what's that? Well, it's kind of like butter. And then these fatty acids with time and warmth turn rancid, and they smell terrible. I mean, not just bad, I mean, they smell ugly. So what we do because of this bacterial infection is we get shake in the lumber or the lumber pieces we cut. Shake is a split that runs with the growth rings, parallel to the growth rings, not across them like a normal crack or something, but shake runs with the rings. And some people call it wind shake, but it's caused because the bacteria weakened the wood. And we get smelly wood. And I could tell you a lot of war stories about dresser drawers and kitchen cabinets made out of bacterially infected wood, and you open the cabinet door and whoa, I mean, it is a terribly obnoxious odor. It also takes longer to dry. Well, again, if the drying people don't know that, they're going to end up with a higher moisture. And what it creates sometimes is wet pockets. The piece of wood is dry, 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 and all of a sudden there's a pocket, maybe 4, 5, 6 inches long, 2 inches wide in the middle of the board, and it's really wet. And it'll dry later, and when it dries later, it shrinks, and then maybe the nice flat surface with that extra shrinkage isn't flat anymore, and so it's called delay shrinkage. And of course, because the wood's weaker, we tend to get checks, honeycomb, end splits, everything, and it is weaker even when we're planing it, so we're going to get planer defects. Planer splitting being one of the more common ones, but there's a bunch of other defects in machining that can develop too. Oh man, so this is terrible wood. Now, unless somebody sees the shake in the normal grading rules we have, bacterial infection alone cannot be eliminated. It is not a grading defect, softwoods or hardwoods. The shake is, that's a separation, that's a split, a crack that runs with the rings, but nothing else. So if you get bacterially infected wood, nobody's really cheating you. It's just they didn't recognize it or they didn't think that it was bad. And the odor can be a big issue with dry products. It's when it's wet, you really smell it, but when it's dry, oh man, then's when you get really expensive issues. The wood is very weak. The bacteria have weakened the wood. That's why it splits and gets the shake in it. So we certainly want to avoid structural application. And it affects finishing. Something in there, and I don't know that anybody knows what it is. If you put a nice white finish on there, whatever's in this bacteria will come through, and that pockets of the finish will look dark and dingy. It'll look dirty. It's really an issue with these light-colored finishes. Well, so much for bacteria. Not much we can do about it except when we see it to eliminate it. Wood density. I talked about how when the wood cell has a thicker wall and less hollow space, we get higher density. That affects the strength. Higher density means higher strength. Higher density means better fastening strength, staples, screws, nails. Higher density also means the pinless type moisture meter, and we'll talk about that just in a moment, is also going to give us a higher moisture than what is actually there. And this higher density, because there's less hollow space, means that machining is going to be different. It's going to be harder to glue and machine. So another factor about wood is we need to make sure the density is in the normal range and not abnormal from what we're expecting, high density or low density. So let's talk a little bit about rough mill yields then. The profit we make is equal to the part value minus the lumber cost minus the manufacturing cost. The point of this, and there's a lot we could talk about this for a while, but maybe another time, but the main point is yield is basically 4 times more important than manufacturing costs. So we need to analyze the quality of our incoming lumber to determine shake, bacteria, and everything. If you see shake, by the way, 100% sure you have bacteria in the wood as well. So one of the big incoming factors for lumber that's going to affect your quality and yield and the pieces in the box even is moisture content. And I suppose most people say, yeah, well, our moisture is 6 to 8% or 10 to 12 or whatever it is. That's an average. First thing I'd encourage you to do is put a decimal point behind that. We don't want to know if it's 6 to 8. We want to know if it's 7.2, 7.1. We want to know decimal points. Second thing is we want to look at the spread of moisture content. We want to know if the moisture has high moisture content or low moisture content. And we also want to look at wet pockets because of this bacterial thing we were just talking about. And some people even look at shell and core as diagrammed here. So there's a lot more to just getting 6 to 8%, which is on a shipping invoice. And one of the things that you can do, the very powerful thing, is to measure the spread of moisture content. This is the number of readings, on the vertical. So the higher it is, the more readings there are going to be. Okay? And then this is the average right in the middle where it says 0. That's the average moisture content. And then if we measure a property called the standard deviation, which is a measure of how much variability there is in the moisture, and so you do this on, say, maybe 30 pieces of lumber or 30 pieces of wood being used for parts, and take and get the standard deviation. the standard deviation, okay, the standard deviation is the spread of moisture content. And you can see here, if we come up with that standard deviation number, if we plus or minus 1, we're actually going to include 2/3 of the readings between -1 and +1 standard deviation. Okay? And then we're going to get 95% plus or minus 2%, plus or minus 2 standard deviations. Okay? Now, how do you measure moisture content? You can use a pin-type moisture meter. The pin-type moisture meter, and that measures resistance and then converts the resistance into moisture content. So we really aren't measuring moisture content, we're measuring electrical resistance. And then this is an external probe that can be used to drive the needles. They're insulated needles, so only the points are exposed, and you can drive them to different depths to get the moisture at the tip of the needle. Many of you are familiar with that pin meter. We also have a pinless meter. The pinless meter doesn't have pins, but it measures the dielectric property of the wood. The dielectric property then is related to moisture content. The pin meter has all sorts of specifications here. It measures only in one spot. It's kind of slow. It leaves 2 little holes. The pinless meter is kind of fast, doesn't leave any holes, but it's very sensitive to density, and it measures an average under the meter rather than at one spot. So basically what one meter does well, the other one doesn't, and what one does poorly, the other one does well. So if you have both meters, that's the way to go. Which is the best one? The one that's used by employees. So which one are they going to use? It should cost over $250, and then it should have a statistical package so that you can get the standard deviation. The pinless is probably the easiest to use, but because, again, there might be a little question at times, double check any bad readings with your pin meter. Again, remember this chart all about wood. Here we have the moisture content and the EMCs related to humidity and so on. We went over that already. And here's just a few examples of some of the moisture issues we can have. On the top we have a panel glued together. It's all 8% moisture content, but we have flat and quarter grain. As it dries, the flat grain will not shrink as much as the quarter grain. So we can get a little lump or bump there. The quarter sawn shrinks more than flat sawn. So again, the quarter sawn, that's in thickness. So the quarter sawn piece here will give us a little bit of unflatness when the moisture changes. Or here's a miter joint. Here I've diagrammed 4% moisture loss. And the angle has changed in the bottom there to 44.7 degrees, which gives us a little bit of opening on the inside. And so again, one of the issues of shrinkage. Here's one last one. Excuse me. Here we've glued a panel together. The water in the glue caused a little bit of local swelling at the glue joint in the second picture from the top. We are in a hurry, so we smooth it out, and boy, it looks great. Come back in a day or two, and now the water around the glue joint has gone down. When the water loss occurs, the wood shrinks just a little bit right in there, and then we get a sunken glue joint, which is the term most of us would use for that defect. And again, here, key variables when machining. And you could go through all these. We could talk about them some other time, but look at the bottom. Wood species, moisture content, and grain direction. So again, what we've been talking about are important factors to especially when they aren't normal as to what we've been expecting. Moisture. One last thing on moisture. Lower moisture means more brittleness. And as a result, you're going to get more tear out, less fuzzing, more warp, more noise. And what do we mean by low moisture? Under 6.5% moisture for hardwoods. But the pin meter doesn't measure that very well, so you have to have a pinless to get this very low moisture. Under 9.5% or maybe even 10.0% moisture content for softwoods would be considered too low for the best machining. Of course, you might say, oh, 9.5 or 10, then it's going to shrink when it comes to its in-use moisture. And that's true, but softwoods shrink half as much as hardwoods. And so in order to get the better machining, we'll tolerate a little bit of high moisture content. Fuzzy grain is the problem if the moisture content is too high. And it could be the rake angle's too small, moisture's too high, or it could be tension wood that we talked about. This one is a good picture of tension wood fibers that were sanded with dull sandpaper. You know, sandpaper has to be sharp. And again, the raised grain problem we talked about, and here's another picture on the right of some raised grain. So what's the goal of a rough mill? To make money, lots of money. And how do you do that? You maximize quality, minimize defective pieces, minimize waste, minimize oopses by understanding about wood. And hopefully that's what we've covered today.